Okay, so here I'm going to sort of follow through the next couple steps in the development of quantum mechanics. These are, I'm a theoretical chemist. My PhD is in computational chemistry. Frankly, it was mostly classical mechanics. But this is super interesting to me. Super interesting to me. But I'm going to, again, try to speak this at a level of detail that is appropriate for an introductory chemistry course. It's important, though, that we look at it and talk about it at least, okay? So we're not going to get super deep. Now, the next couple steps. First of all, Werner Heisenberg, German, determined there's a fundamental limit to, this is bizarre, I say that a lot, don't I? How accurately one can measure both the position and the momentum simultaneously. There is a limit, okay? And it's called the Heisenberg uncertainty principle. The more accurately we measure the momentum, the less accurately we can determine its position as at that time, and vice versa. This is the Heisenberg uncertainty principle. It says it's fundamentally impossible to determine simultaneously and exactly both the momentum and the position of a particle. All right, so here's how it's described. The range in which x is, the range in which x, right? So it's some kind of an area where x is. That's the uncertainty of the position of the particle, x, and times the uncertainty of the momentum of x, right, is greater than or equal to Planck's constant divided by 2. Okay? The area that we can find it in and the momentum in which it can be is greater than or equal to h bar over 2. All right? So that's the uncertainty principle. You can imagine that if we were going to find its exact location, we would find that delta x would be 0, right? And so that can't be, because it can't be greater than or equal to h bar over 2. And we can't find its exact position either. I'm sorry, its exact momentum. Because if we found its exact momentum, then the range of possible momenta would be 0, right? If we knew its exact momentum. All right, that's a little bit bizarre, but I think we'll leave it at that. So the next scientist to come along was Erwin Schrodinger. He extended de Broglie's work by incorporating the de Broglie relation into a wave equation, and this is known as the Schrodinger Equation, which we've got coming up in a future slide. It's way more complicated than we need to get into for this course, but I do want you to see it. You should see it. The Schrodinger Equation, Schrodinger properly thought of the electron in terms of a three-dimensional stationary wave, right? It's a wave function. So he thought of it as a wave, and so he gave it a wave function, and it's oftentimes represented by the Greek letter psi, right? Which I'm going to write like that. A capital psi is like that, and a lowercase psi is there, but there it is in a font, in a typeset by PowerPoint. Okay, so the wave function is given as a psi. It's a function. It's a three-dimensional function. And a few years later, Max Born said, wait, electrons are particles. So the waves represented by psi are not physical waves, but instead they're probability amplitudes. Okay? And so he figured out that the square of the magnitude of the wave function, so if you take the wave function and you square it, you're going to get the probability of a quantum particle being in a certain location in space. Okay? So basically, we're going to find out roughly where the electrons are by looking at their wave functions. By squaring their wave functions, we can find the probability of where they are. Okay, wave functions can be used to determine the distribution of the electron's density with respect to the nucleus in an atom. And you'll hear that language out of my voice a lot, or out of my mouth a lot. This semester, I don't think you're ever going to really need to understand it deeply, but there it is right there. Wave functions can be used to determine the distribution of the electron's density with respect to the nucleus in an atom. We think of electron orbitals as being like clouds, right? Where they're more dense, the cloud is more dense, where there's a greater probability that the electron's going to be. We find that probability by looking at the square of the wave function. Okay, so here's the Schrodinger equation. It's beautiful. In its most general form, the Schrodinger equation can be written as such. Okay, this is like a caret. It's h hat. Psi is equal to E psi, where E is the energy. H is an operator. This is a list of or series of mathematical operations, and this is a function. Okay, so you take this function, you multiply it by, or you do all these it's not a multiplication. There are some multiplication, some addition, and so on. You take these operations and you do it on that function, and then you factor out the function, and boom, you've got the energy. Yeah, I know. That's weird. I didn't do this successfully until I got to graduate school and really just fell in love with it then, but it's bizarre. Okay, H hat is the Hamiltonian operator. It's a set of mathematical operations, and it represents or gives the total energy of the quantum particle. The wave function is given by psi. That's the wave function of the particle that we're interested in. If we want the energy for that particle, then we're going to use psi for that particle, and we're going to do the Hamiltonian that's appropriate for that particle, and E is the total energy of the particle. All right, so Schrödinger's work, as well as that of Heisenberg and Born and many others following in the footsteps, is generally referred to as quantum mechanics, and that is our introduction to quantum mechanics. All right, hope that's helpful in some way. I know that there's more there than we can possibly appreciate in a course like this, but it is cool. It's important that you see it in a college chemistry course.